Hi everyone! In this lecture, my colleague Chiara and myself will introduce the main concepts concerning the basic data structures for vector and raster models. In this slide, we have put the lecture outline. As you can see, we will first present a short introduction concerning the representation of the real world by way of raster and vector models in a GIS environment. Then we will describe in detail the characteristics and the file formats that are typically used for rasters and vectors. For both models, we will show how to import a file in the software QGIS 3.10. We will then present a comparison between vector and raster models, with guidelines regarding how to choose the adequate model for the main applications. Finally, the GeoPackage format shall be introduced. The main characteristics and advantages of such format will be presented. And we will also explain how to work with GeoPackage format in QGIS 3.10. Now let's have a look at this short introduction concerning the way of representation of the real world in a geographic information system. We can say that geographic information systems are dedicated to the georeferenced information. This kind of information should be structured according to standard models in order to be stored on an informatic support. As you can see in this slide, there are mainly two ways to represent the spatial component of information in a geographic information system. First, we have the raster model. Then we have the vector model. These two models are used to represent real-world objects or features that, generally speaking, can be divided into two abstractions. On the one end, we have continuous fields, for example, the ground elevation or the land use of the territory, that is, all the elements characterized by a continuous spatial variability and that can be modeled as a continuous surface. On the other hand, we have discrete objects, for example, a tree or a river, that is, all those elements that are modeled by means of simple geometric elements, a point, a line, and a polygon. In particular, in the raster data model, the information is represented on a regular grid of cells, typically squared, that are called pixels. Each pixel of the matrix contains an assigned numeric value that represents any kind of information that has spatial reference. For example, as you can see in the first picture here on the right, the raster model may be used to represent the ground elevation in a study area. In the vector data model, the feature boundaries are defined by pairs of coordinates or triplets of coordinates in the three-dimensional case. Each coordinate refers to a specific location in the real world. Each feature may be represented through a point that is defined with a single xy coordinate pair, a line that is defined by two or more linked xy coordinate pairs, or a polygon that is defined by a closed line constituting the polygon boundaries. In the second picture on the right, you can see how the vector model can be employed to represent discrete geographic elements. For example, a river can be modeled as a line, a lake can be modeled as a polygon, and trees may be represented through points. As you can see in this picture, both vector and raster models can be used to represent any kind of geographic element in the real world. For example, in this case, we have a building and a road. With the vector data model, the building has been represented through a polygon, and the road has been represented through a line. While in the raster data model, we can see how each element has been represented with a group of pixels. Nevertheless, we can say that one type of representation can be more appropriate than the other depending, first of all, on the particular type of geographic data that is being represented, and also depending on the particular analysis that has to be performed. We can now talk more in detail about the raster data model. As I have previously mentioned, in this kind of model, the information is stored in a matrix that is made up of elementary cells called pixels. The term pixel stands for picture element, and in fact, a pixel represents the smallest unit of an image. Each pixel stores, generally speaking, a single value, but in case the raster is used to represent an image, the pixel stores a combination of three different values according to the red, green, blue color composition. In order to define completely the raster georeferencing, the coordinates of one vertex and the spatial orientation of the matrix must be fixed. This means that we have to know the two coordinates of a vertex and a single coordinate of any other vertex. In this way, the position of any other pixel can be derived from its row and column numbers and from the pixel dimensions. The data types that can be represented according to the raster model are mainly three. First, we have digital images. Each pixel stores the information used to represent either a picture or a photograph or a satellite image. In the first case, three different values must be stored in each pixel, according to the red, green, blue color composition, while in the second case, a single value for each spectral band must be stored. Thematic maps can be represented through the raster model as well. In this case, each pixel stores the information used to represent a geographic element, such as the land cover or a physical phenomenon that has spatial variability, such as a temperature distribution or the concentration of a pollutant. Lastly, in case of digital terrain models, each pixel stores the information relative to the height of a specific portion of territory. The picture on the right shows examples of data that may be represented as a raster file. We have a digital image acquired with a digital camera, a thematic map showing the land cover in an area, and a DTM that shows the ground elevation of the territory. The spatial or geometric resolution is an important property that characterizes raster data. It is associated with the number of pixels per unit of length, or equivalently to the number of columns and rows that constitute the raster. It is particularly important because we can understand that the higher is the spatial resolution, the higher is the level of spatial detail that is provided by the raster, as well as the memory space that is required to store the information. It is possible to apply compression algorithms to reduce the physical space necessary for the raster storage. We have two main types of compression techniques. On the one hand, we have lossy compression formats that imply loss of information. On the other hand, we have lossless compression formats that prevent loss of information with respect to the original raster. Lossy compression formats imply a lower file size, and therefore they are suggested for the image transfer. Lossless compression formats require less space with respect to the original file, but they keep unaltered the original information. In the picture reported in this slide, the effect of spatial resolution variation is presented. We can see that the larger is the cell size, the lower is the spatial detail of representation. But at the same time, faster will be the image display and the image processing in a GIS environment. Besides, we can say that the larger is the cell size, the smaller will be the file size, and therefore the space of memory required to store the image. Now let's have a look at the existing formats that are used for the raster models. The first one is the Esri grid format. Actually, there exist two types of Esri grid. The first one is a proprietary binary format that is also known as arcinfodata. In this format, the raster is stored in several files that are contained in a set of directories. Actually, two directories, at least two directories, are needed, and they are called name and info directories. In this case, the grid name must satisfy some conditions. In particular, the grid name must begin with an alphabetic character, and it can only include alphabetic and numeric characters, as well as the underscore. The second format is a non-proprietary ASCII format that is known also as arcinfo ASCII grid. In this case, the grid is stored in a textual format, and it is characterized by a header that contains the number of rows and columns, the coordinates of a vertex, the size of a single cell, and also the numeric value of each cell. These numeric values are stored and listed row after row and from north to south, as shown in this picture in the slide. Another well-known raster format is the GeoTIFF, where GeoTIFF stands for Geotagged Image File Format. It is a format extension that allows the storage of georeferencing information in a compliant TIFF file. In particular, these information concern the data projection, the coordinate system, ellipsoid, and datum. This format is very well known because generally it is used to store satellite imagery. In any case, it includes the header tags that contain information about the image geometry, such as the image size, definition, arrangement, and compression. A very important characteristic of GeoTIFF is that it is a lossless compression format, and therefore it doesn't produce loss of information. Furthermore, it supports either black and white, grayscale, pseudo-color, and true-color imaging. The third raster file format that we are going to present in this lecture is the ERDAS Imagine IMG file format, where ERDAS stands for Earth Resources Data Analysis System. ERDAS IMG is a proprietary file format that originally was developed to be used with the ERDAS Imagine, a software meant for the processing of remote sensed data. We can say that the main characteristic of this format is that it distinguishes between two different raster layers. A continuous raster layer that is used to represent an image acquired by a sensor, and a thematic raster layer that is used to represent a specific theme or a specific subject. In the first case, the value stored in each pixel may vary in a continuous range because it can represent, for example, temperature, elevation, or radiance. In the second case, the pixel stores a single value, that is a numerical code corresponding to a particular category. This format has its own binary format for images, and being linked to a commercial package, we can say that it is not an open format. Interoperability is therefore limited, and this is why it is generally recommended to export the data to an open and wider supported format, for example, the GeoTIFF. Another important raster file format that I'm now going to present is the NetCDF CF file, that is characterized by specific metadata conventions. The name stands for Network Common Data Format Climate and Forecast. Originally, it was developed especially for model-generated data, in particular for atmospheric models. But now it is becoming quite important for many other environmental applications, and in particular for the representation of observational data. It consists in a binary storage in open format, optionally with compression. The main characteristic of a NetCDF CF file is that it is characterized by two different sections. First, we have the header file section that contains dimensions, variables, and global attributes. And in particular, for each variable, the header specifies the data type, the unit, the content description, and the value of missing data. Then we have the data section that contains the actual value for each dimension and for each variable that is listed in the header. The last raster file format that we are going to introduce in this lecture is the JPEG 2000. At the moment, it is the most widespread open source raster format. It is a compression standard that was developed by a joint photographic experts group committee, and it is used to maintain the quality of large imagery. In fact, the JPEG allows for a high compression ratio and also fast access to a large amount of data at any scale. It is used for either color and black and white images, and one of the main advantages of the JPEG is that it allows both lossy and lossless compression. A raster file may be very easily imported in QGIS 3.10. It is simply necessary to use the Add Raster Layer option that is in the Layer menu. As you can see in this slide, this function opens a window in which the user can select the raster that has to be imported. It is simply necessary to click on the ellipsis symbol and select the correct work directory. It is possible to set the file path and in particular to select the raster format that the user is looking for. Following this procedure, the raster file is added as a new layer in QGIS, and as you can see, it is displayed on the right. In this case, I have imported a GeoTIFF file that represents the digital terrain model of the Maputo area in Mozambique. The procedure that has been shown for the file GeoTIFF can be used to import any other type of raster file format.
So far we have discussed about raster data models, therefore now it is turn to speak more in detail about vector data models. We are going to start now by their generalities and then we will focus on their different data formats. We already mentioned that vectors represent real objects as discrete entities through points, lines or polygons. We can see here in the figure an example for their application for the field of urban planning. As you can see here in our example, points represent the roundabouts of streets, and lines represent the streets and polygons the neighborhoods. Therefore, from this example, you can see that points tend to represent small geographic features, as could be location of trees, depth, points of interest, and so on. And each point is defined by just a couple or maybe triplet for the 3D case of X, Y, and Z coordinates, representing a single location. Therefore, points have no dimension, so if I take, for example, my roundabout that is represented with a point, on the map I can no more see its area or its shape. Therefore, then if we go to the lines or polylines, here they represent streets. However, they can represent all linear features as it could be for rivers, roads, railroads, pipelines, and so on. And how to define a line? A line could be defined by a path that links all coordinates of the points that are called vertices. And therefore, lines have just one dimension, that is the length, that could be measured also through GIS. Then we still need to mention polygons. Polygons here represent neighborhoods in our example. However, polygons can represent all features, all geographic features that have an area, and this area is bounded. Like it could be for lakes, parks, buildings, and so on. Polygon borders are defined through lines whose first and last vertex coincide. And polygons have two dimensions, therefore area and perimeter, that could be again measured through GIS. Finally, all these features that I have mentioned, they can be separately grouped into different layers. Each layer will contain features of the same geometry type, and each layer will represent a particular thematic information. For example, here in figure, I could take all the lines representing the streets, and if I group them into a layer, this layer will be the one that will store the information about the streets. Moreover, when we speak about vector data models, we cannot forget to mention attributes and database that are an important characteristic of vectors. Indeed, each feature of a vector layer is stored in a database where linked to it there are also its coordinates and attributes that describe each feature. Attributes that can be first a specific ID to easily recall each feature, and also can be thematic attributes as the name of each feature. To make you easily understand, I have put here an example taken from your exercises. It is the Mozambique Administrative Provinces Boundaries layer. You can see from the picture it is a polygon layer and it has 11 features. These 11 polygons, if I open the attribute table, are described through these 11 rows of your attribute table. And the columns here store the different attributes of your vector layer. So you will have each feature described from, for example, its area, its particular code, its name, or also the nation it is referred to, as in this example. So far we have described the generalities of vector data models, therefore it is time to focus on the different data formats that can define a vector. Shapefile, maybe you have heard about it. It is one of the most popular vector data GIS format. However, it is not the only one. Therefore, we will start now speaking about it, but then we will mention also other data formats. Therefore, Shapefile has been introduced with ArcView GIS version 2 in the early 1990s, and it is now developed and regulated by Esri as a mostly open specification for data interoperability among Esri and other GIS software products. What makes Shapefile really common, it is that it is really easy to be read and written with a wide variety of softwares, and it is in a binary format. Shapefile format can spatially define vector features as points, lines, and polygons with their coordinates, and each item, each feature has attributes that describes it. However, a limitation of Shapefile is that it cannot store topological information, thus it cannot store information about the relationship, the spatial relationships between the different items. Still need to mention an important characteristic about shapefiles. Indeed, when we talk about a shapefile format, it seems that we are talking about just one file. In reality, it is not as it seems, because a shapefile format consists of a collection of files stored in the same directory. From this collection of files, 3 are mandatory. What does it mean? It means that if I want to send to someone else my shapefile vector, I need to send at least these 3 files. It is not sufficient to send, for example, just the main file, that is the SHP. These 3 files, each of them has a role. The SHP, for example, stores the geometry data. Particularly, each record of this file describes a shape with the list of its vertices, therefore its coordinates. Then there is the SHX, that is the shape index file. It is needed to allow seeking forward and backward quickly to defeat the different features. It contains indeed a positional index for each feature geometry. Then there is the DBF. The DBF stores the database table, and it is devoted to store, therefore, the attributes of each feature. Therefore, there will be the attributes that will be linked to their features with a one-to-one relationship attribute feature maintained by the index of the feature. Therefore, again, the SHX file. Therefore, all these three files are needed, but there are also other files. These non-mandatory files can be, for example, the ones that I put here in this slide. For example, there could be the PRJ, the CPG, or XML files. Each one, as for the mandatory files, is needed for a specific role, to store a specific type of information. For example, there is the PRJ that here you can see the example from your exercises, again from the layer about the provinces boundaries. It stores the projection description of the vector layer, therefore the coordinate reference system. If you do not have it with your vector files, you could not have it, but when you will open your layer on QGIS, you will see that you will get an alert message telling you that your layer do not have any coordinate reference system, so that it has to be set. Then also the CPG is another file that is needed to specify the code page for DBF. Then your data could have also an XML, therefore a metadata file. This metadata file again is readable. Indeed, it is an XML, and it stores, for example, the data from the author of the data. Or for example, you can see here also in the yellow rectangle, there are also the minimum scale or maximum scale that the vector layer is suggested to be looked at. And so on. There are also other files that here I did not mention. And that's all for the shapefile format. As I mentioned, it is a very common format, and you will see it also in your exercises. However, this does not mean that it is somehow the best choice. Indeed, it has some limitations due to its format, and I want here just to recall some of them. Starting by spatial representation, we talked about the points and their coordinates to define lines and polygons. However, we did not mention that the spacing between these points implicitly determines the scale at which the feature is represented. If I take, for example, a river that I want to represent, and this river at a certain point gets a smoother shape. So I will have to remember that shapefile format does not support splines and circular arcs. That means if I want to achieve smoother shapes, I will have to add more points, and this will require also more data storage. Speaking about data storage, another limitation is that SHP and DBF component file cannot exceed 2 GB. It is an ESRI restriction. Moreover, the table format for the DBF component file is based on an older database standard that supports field types as floating points, integers, dates, and tests, however, with a maximum character storage that is limited. For example, for floating points, I will have maximum 13 characters. For integers, depending by they are long or short, 9 or 4 characters at maximum. For dates, maximum 8 characters, and for text, a maximum of 254 characters. Then another important limitation for shapefiles is that, differently from other vector formats, they do not store topological information. That means they cannot store information about the spatial relationships among the different entities of a layer. And finally, another important limit is that when I send or receive a shapefile, the style is not stored in the vector data files. Therefore, the receiver cannot see how the sender intended him to look at the vector data. So far we have discussed about shapefiles, so now let's focus on the other types of formats for defining vector data. A first example could be KML, Keyhole Markup Language, which was first developed by Keyhole Inc., that was later acquired by Google. Today, indeed, it is primarily used for Google Earth, and it is an international open standard of the Open Geospatial Consortium OGC. KML is an XML file so that it can be easily manipulated as well as read by any text editor. Moreover, it was born as a format for 2D and 3D spatial visualization. Indeed, it can define a very interesting set of features like place marks, images, paths, polygons, 3D models, and textual descriptions. And here I have put in the images some examples taken by Google Earth. First, at the top you can see a placemark with its description, and then under, in the second picture, you can see a 3D visualization of a building with, attached to it, a photograph of the building itself. Moreover, KML therefore uses 3D geographic coordinates. It needs to be defined for every feature, longitude and latitude that need to be defined according to WGS 84 coordinate system. You can define also the altitude. If you do not define it, it will be set by default as clamped to the ground. And altitude will be referred to the EGM 96 geoid vertical datum. Moreover, in KML language, you can use also negative values for defining, for example, coordinates in the west or south. Finally, usually you can find KML with an extension KMZ, which easily corresponds to the KML zipped version of the file. Another vector format is GML, Geography Markup Language, that is, as KML, an XML-based open standard format, and it is used for GIS data exchange. It is often used in WebGIS and cartographic services, even though it tends to be sometimes very heavy as a format to be processed. It is defined by OGC, and again, being an XML-based file, it is easy to be modified and read in a text editor. In GML, features are different from geometry objects. It means that while a feature represents a physical entity, for example, a building, a geometry object defines a location or a region, and it can be associated to a feature as an attribute. Therefore, attributes can be also the coordinate reference system that for GML has to be explicitly specified differently from KML, as well as attributes can be also topology and time. A feature that can be also a coverage or a sensor data that does not only the conventional vectors, can have linked to it also text, videos, or photos, and it is also this that could make GML very easy as a format. Another interesting format, different from the previous ones, is GeoJSON. It is particular because it is an open standard format, but it has been written and it is maintained not by a formal standards organization, as it could be UGC, but by an internet working group of developers. GeoJSON is based on JavaScript object notation, JSON, and it is a lightweight geospatial data interchange format. In particular, it is used by many open source GIS packages, and it has been designed particularly for representing simple geographical features along with their non-spatial attributes. Therefore, in GeoJSON, geometry and features, as you see also in the figure, are different objects with geometry that represents a region of space, thus storing geographic coordinates as longitude, latitude, and altitude, while features are spatially bounded entities that can be also non-physical entities. Geometry primitives can be points, lines, or polygons, but also group of points, lines, and polygons that are called multi-points, multi-line, string, and multi-polygon. These have to be considered as just one entity. A feature can be defined by geometry and addition attributes, and a set of features is a feature collection object. Interesting here is that features stored in one feature collection and not to be all of the same geometry as it could be for the traditional shapefile. They can be, for example, one feature with a point geometry and one another with a polygon geometry, all in the same feature collection object. So we have mentioned some interesting GIS vector data formats. Now I want to speak, as it has been done for the rasters, about how to import vector data on QGIS. The procedure is simple. If you have a vector layer you want to import, just go to Layer, then Add Layer, and then also Add Vector Layer. It will open a window. This is the window where you will have to insert the directory of the layer you want to import. So you can go to the ellipsis symbol, then click there, and if you want you can search also for a particular type of vector format. Then when you find the desired vector you select it and you will see its directory here in this window. You can see, for example, I have chosen for this example again your exercises shapefile for provinces of Mozambique, and you can see here the SHP that represents the vector data format that is a shapefile. However, this works for all types of vector data formats you want to insert. Here you can see how the layer looks like on QGIS once it is imported. So in the end we have separately talked about raster and vectors, and we want now to compare them looking at their advantages and disadvantages. If we start from rasters, we can say that they are good for storing image data and representing reality in a continuous grid of pixels, They are good also for surface analysis. Their data structure is simple, however, this does not mean that they require less storage space. Indeed, their dataset can be very large depending by their cell size does to their level of detail. Also, they cannot store topological information and it is difficult to perform with them network analysis. However, their matrix structure allows different attributes to be stored in the same grid cell that makes easier certain types of spatial comparisons between rasters. And also, then a disadvantage is that when I use large cells, therefore a large cell size, I can lose some information. Then, if we go to vector data models, we can see that since most information as maps is represented with discrete object, therefore no data conversion is required when we want to use the vector format. Also, they have a compact data structure, that means less space for storing data. And this data structure, however, is complex. That is a disadvantage. Indeed, they need that every vertex is explicitly located. Therefore, we need to know each coordinate. And also, the vector data models are very good to perform network analysis, and also they are good to store topological information, but they are inefficient to represent high spatial variability, and it is also difficult with them to perform filtering differently from rasters. So, in the end, there are no fixed rules to choose between rasters or vectors. It depends by the object you want to represent and by the aim. For example, do you want to simply display data or you want to perform some analysis? And which type of analysis? You need to think to this question when deciding. For example, rasters can be generally better to show spatially distributed phenomena, while vector could be better for network analysis. Or also I could consider also that for the same accuracy, vectors can require less storage than rasters. However, rasters, for example, with raster calculator, could allow faster elaborations on data. With vectors, then I could look at spatial relationships, thus to topology, while with rasters, I could easily compare different characteristics stored in different maps of the same areas. So, in the end, choose carefully and remember that conversion from one model to another is possible but not recommended. It is better to keep it at minimum, as every conversion adds some error to the map. Remember also that if you choose raster data models, you need to constantly take into account their cell size.
Now let's have a look at another quite important file format that is called the GeoPackage. This file format is becoming more and more used, especially in the last years, as an alternative to the traditional raster and vector formats. We can describe the GeoPackage as an open, standard-based, and platform-independent format, but other important characteristics are that it is portable, self-describing, and compact. We can think of the GeoPackage format as a sort of geographic and tabular information container. Particularly, it can store vector features, file matrix of imagery, raster maps, and various extensions, all within an SQLite database. The GeoPackage standard defines certain characteristics that the GeoPackage format must have, in particular the table definition, integrity assertions, format limitations, and content constraints. The use of the GeoPackage format has many advantages. First of all, it is an open format based on OGC standards and designed to store complex and large data. GeoPackage is the default format for QGIS 3.0. Unlike, for example, the shapefile, the GeoPackage is a single file that has extension GPKG. Therefore, it is preferable for transferring geographic data because it facilitates interoperability. The data can be accessed and modified directly in a native format. So we can say that the GeoPackage supports the direct use. Another important advantage is that the field's name in the GeoPackage file can be longer than 10 characters, while the textual attributes can be longer than 255 characters. In any case, the main advantage of the GeoPackage is the possibility to save the file symbology directly within the GeoPackage file. So the style is not saved in another file, as happens, for example, with shapefiles. Now we are going to see how to work with the GeoPackage format in the software QGIS 3.10. First of all, how can we create a GeoPackage file in QGIS? As you can see from this slide, we have to press the function new GeoPackage layer that is identified by the small box symbol that is present on the main menu. The window that opens up allows the user to set the file path, the file name, and the file extension. The table name in the database can be defined as well. Moreover, the user can specify the geometry type and the data projection. As you can see, in this case, we are creating a GeoPackage that is characterized by no geometry, as we will fill the file later on. Once we have created the empty GeoPackage file, we need to add a new connection to the new GeoPackage. And it is possible by simply clicking on GeoPackage New Connection and selecting the right directory, as shown here on the left. Now that we have created an empty GeoPackage file and we have added a new connection to this file in QGIS, we can add different types of data and import them into the GeoPackage. First of all, we need to import in the QGIS project the data that we want to import into the GeoPackage. For example, we can import a shapefile and a geotiff file. The user has simply to drag and drop these two layers into the GeoPackage connection, as you can see here on the left. There is also the possibility to save the symbology of the two layers contained in the GeoPackage. Once the style of the shapefile is set, the user has simply to select the option Save Style, and in particular Save in Database GeoPackage. In this way, every time the GeoPackage will be opened, the shapefile will have this symbology. In this slide, you can see the final result. We have the new GeoPackage file that contains two different files. In particular, a shapefile that represents the administrative boundaries of Maputo province, and a geotiff file that represents the digital elevation model of the same area. This was actually the last slide. I hope that everything is clear, and I thank you for your attention.